Okay, let's start our seminar. Yes, let's discuss this bijection between Ext1 and a set of isomorphic classes of extensions of the form n x m. Modular isomorphism which is identical on n and on m. Construction. You used construction from the seminar, from the lecture, yes? Oh yes, okay. Then construction. If we have what the class of Ext1? If we have m, we consider the beginning of the free resolution. Free resolution of m. We can choose some generators of m. It's surjection from free module. Then we consider some basis of relation. It's surjection to the kernel from some other free module, and then relations between the relations, and so on. And then it's d0, d1, or maybe yes, it's d minus 1, maybe yes. I don't remember. And if we have n, then element from Ext1 from m to n, it's homomorphism from f1 to n, such that this composition is 0. Yes, modular this composition. Yes, it's some xi such that xi d1 is 0, modular plus phi d0, where phi from f0 to n. No, maybe, okay. And if we have such element, we can consider extensions of the form x is n plus free module. Yes, of course, no. We need some basis and some relations, yes. Of course, of this particular free resolution. If we have that f0 is free module with basis ei, f1 is free module with basis, it's gi, yes, it's generators kind of. Gi, rj is relations, and f2 is cg's, the first cg's, sk. And d0, d minus 1 sends gi to some generators mi, d0 sends rj to some basic relations between basis of f0, yes, gi, ji. And d1 sends sk to some relations between relations, sigma k j rj. Okay, and then if we have some class, we can consider x is n plus some free R module with basis, which is in bijection with these generators, yes, and modular relation that xi of n is equal to. We need some elements from. Yes, it's not from n. It's from fi. So it's rj. Yes, it's from rj, and then it's equal to rho ji ei. These relations, and then we have map from n to this module. We have map from this module to m, and in fact, this is short exact sequence. This extension. It's the map from the left to the right, and other direction. If I have extension, then I need something like this homomorphism. It's just okay. I need to understand what is the xi of rj. I consider my generator Mj, consider any pre-image, yes, in X. Consider relation Ij. Yes. Sorry, Mi, it's I. Mi, Xi, Ji, Xi. It goes to relation in M, which is 0. It's basic relation. So it's element from N. No, and yes, and Rj goes to this element. This is this element. Okay? Yes? It's element from N because it goes to 0 in M. No, and proposition that statement that this is correct maps, and this is bijections. It's bijections, inverse to each other. Okay. No, before you show us the check of this fact, yes, the proof of that this is bijection and all is correct, yes, you can show us this. Before this, we maybe can reformulate this map. No, this map more or less straightforward, just extension. This checking is not very hard, in fact. Yes, check that this is extension is not very hard, in fact. And even if you consider if you consider other representing cycle, it's not very hard to understand that it's isomorphic extension. More subtle thing to check that this map from extension, that this class does not depend up to homology from extension. Yes, it's more subtle checking, I think. Yes, am I right?
I guess.
And we can reformulate in more abstract, more coordinateless terms this map. 1 second. No, in fact, we can reformulate it in just one string, one row. If you have an extension, let's just consider the long exact sequence in Ext and Hom. For example, for Hom, apply Hom to N. Okay? Apply Hom to N or R. Then what we obtain? We obtain exact sequence, long exact sequence in the opposite direction. We obtain 0 Hom M to N, Hom X to N, then Hom N to N, and then Ext 1 M to N, and image of ID is our class. In fact, it's image of identical map. This is element corresponding to this extension. In fact, it's the same element, the same class. And from this definition, it's obvious that it's correct. It's correct homomorphism of group. It's correct element. Okay, so we don't need to check correctness. We only need to check that this direct definition coincides with this abstract definition. Okay. Dually, you can consider Hom from M to the short exact sequence, and then you obtain exact sequence 0 Hom N M to N, Hom M to X, Hom M to M, and then again Ext from M to N, and it's also image of identity. Okay. So to check correctness, in fact, you can check it directly, but also you can check that. But here you need the concrete construction of the boundary homomorphism. It's this construction. You need concrete boundary homomorphism, and you can check that this boundary homomorphism is exactly this. Exactly. No, I cleaned it. Exactly the class which was here before. Exactly this class of this homomorphism. Maybe let's check this. That this is coincide. Okay. And then you show us that this is exact sequence. Okay. Maybe. Okay. Let's try to check that this boundary homomorphism sends identity to the class which I write down again. What?
Why do we need two maps? I mean, when we
No, it's anyway. You obtain the same thing. I will check that this thing we can check if you apply this thing, you need projective of free resolution of M, which we use here. For check this thing, you in fact need injective resolution for N. It's dual construction. You can also consider injective resolution for N, and then consider something from M to something like this, and you have a dual construction. In fact, it's from this thing. This thing corresponds to this construction from free resolution of or projective resolution of M. Okay, and we will check that this is correct. But no, it's also correct. Yes, it's correct homomorphism. We only need to check that in some concrete terms it coincides with this concrete definition. Okay, they coincide. It's from injective resolution of N. This is from projective resolution of free resolution of M. This. Let me recall the definition of concrete Xi. It's this map. I have extension. I consider some concrete resolution, free resolution of M. I have generators EI or GI. It goes to some generators MI. I consider some preimages Xi, and then this element in fact lies in N, and this is image of Rj. Now let's check that this. No, it's easy to check that this is the composition Xi or D1 is 0. It's more or less easy. Yes, you can check that it is easy from exactness of this resolution, more or less. So it's really homological class. So we have this element from Ext 1 M to N, and we only need to check that in fact this element represents the class which is the image of identity under the boundary map. Okay. Now, here we need to directly understand what the boundary map is, very concretely, very directly, in terms of some resolutions. Okay, let's do this. It's also some kind of checking, but maybe a little bit less tedious than yours. No, and maybe it's a little bit more pretty reformulation of this. Yes. Okay. Okay. Let's clear this part. How we obtain the long exact sequence of Ext? We have short exact sequence of our extension. We consider some free resolution, or some resolution of M and some resolution of N. We choose some concrete resolution of M. Okay, let's use it, F0, F1. Then we need to choose any projective resolution of N. And then you can construct from them the projective resolution of X, which as modules in each level, it's a direct sum of modules Pn and Fn, yes. But how differentials works? How differentials works? Okay, you define this module. You need to map from this module to X. No, you already have map from P0, it's just composition. But you need map from F0. And this is some lift of this map. You have map to M, and this surjection you have some lift. No, it's exactly the choice of preimages of, no, we have basis Gi. It goes to Mi, and this is exactly the choice of preimages, yes, this map. So we can use preimages Xi. So this map, D minus 1. D minus 1 sends, no, P is from P0, and sum of, no, with some coefficients Gi. It's, no, I have this map, no, in fact, no, okay. We maybe need some names. Okay, it's pi, I, dn minus 1, dm minus 1. Okay, this is d, it's composition I, d minus 1 n of pi plus alpha e xi, okay? This is just composition, this is just composition. And this is lift. I have element ei, it goes to some element in X, which goes to mi under the projection. And this is choice of preimages. Okay, let's choose this preimages xi. Okay? This defines you the map from F0, and this is map from this summand. It maps Gi to Xi, and it goes to Mi. This map Gi goes to Mi because we know this concrete resolution. No, so this, no, okay, yes. D of P is just I d minus 1 of P, and d minus 1 of Gi is just Xi. Okay? This defines you the map from direct sum, okay?
Okay.
It's not just direct sum of these two differentials. It's some kind of, it's because, so this projection resolution is not direct sum of chain complexes. It's direct sum as modules in each level, but differential is not just direct sum of differentials. It's some kind of gluing of them. Okay, and then we have kernels of these maps. They have kernel 1, kernel 2, kernel 3, and they also fit into the short Ext sequence. And here we have projection from P0 by definition of projection resolution. Here we have projection from F, or from P1 to from F1, and we also doing the same thing. Okay, let's do this. We need to understand what this kernel. It's not direct sum of two kernels. This short Ext sequence is not splitting in general. It's some module. No, okay, we have this map, this explicit formula. No, okay, if d minus 1 of p sum of some elements of basis of F0, if it's 0, on the other hand, it's no, let me ignore I because it's just inclusion. Yes, I will write just d minus 1 for n. Okay, for n. Okay, it's d minus 1 for n of p, no, plus some elements alpha I xi, and this is 0 in X. And what does it mean? This means that at first that this element in n, because this is in n, this is in n, because it's image of these differentials goes to n. So this element in n, so it's in kernel of M. What does it mean? Okay. No, if I apply pi to this sum, alpha I xi, I obtain 0. On the other hand, pi of xi is mi. I know this because this is gi to xi to mi. It's this map, yes. No, it's just d minus 1 of m. So this is just d minus 1 of m of alpha I gi. Yes? Okay? This map is just this map, composition. okay? No, it's alpha IMI is 0, and this is by definition, okay? But so it's in kernel of this map. I know this map is just image of F1. So in fact, this means that this direct sum, this sum is just d0 of M. No, this is d0 of some sum. I don't know how to say it more tricky in English. Some sum. Как сказать? Некоторая сумма. Some sum. No, of some beta g rg. Because it is the kernel, yes? Okay? Do you agree? No, do you agree? Okay, no, I know how d0 acts on rj. I have some basic relations. No, so it's some relation. In X, it's some relation in M, so it can be, I just want to say that it can be expressed as sum of some basic relations. It's what I want to say. It's image of Pj, rho, ji, ji, and this is basis. This ji is basis, so in fact, these things are sums of this form. So in fact, this is equivalent to say that coefficients, or maybe yes, coefficients are sums of coefficients of basic relations. Okay? Because it's basis. So what I want to say is that no, basic relations is the basis of the model of relations. We have some relations. In fact, all of this relation is sum of this expression of no, it's some linear combination of basic relations. Okay. Any coefficient in my relation is linear combination of coefficients of basic relations. Okay. By definition of my free resolution. Okay. This means that, in fact, this element is of the form. So what I obtain again, d minus 1 n of p plus here I have some beta g rho gi xi ji. That's 0. Okay. Maybe it's enough for us because no, okay, maybe let's remember this. I'm going to clear this part of the board. We obtain that if we have element of kernel, then no, it's some submodel of this, and it has 2 coordinates, and on the second coordinate it has this form. It's what I want to say, more or less. More or less. Sorry. Sorry. No, yes, it's true, but here it's element of it's element of X, but element of kernel. Where is element of kernel? I have P. What if P sum of alpha ji is in kernel, in the second kernel, the middle kernel? Then this thing has this form, at least. No, then this is true. Yes. Okay. If it's in kernel, I think it will be enough for us. Okay. Okay. Then let me clear this thing. No, because yes, no. Okay. Let's finish the understanding of this differential. So what we need here, we have some composition here again, and we need some lift here. How we can define it? It has basis rj, and we need we need some map, which if we consider composition to kernel 3 and then to F0, it's just projection on the second direct sum. Okay. This is projection on F0. It's some kernel, it's some submodel. It's not maybe direct sum, but it's submodel, and we have projection on F0. And this map is just this projection. we need some map from F0 to this kernel such that this composition coincides with D0, okay, of M. No, it's definition of this lift, okay? No, and we see how the second coordinate always look как-то выглядит, seems always. We see the form of this second coordinate. So it always have this form. And so we can define this map, this lift. I don't know, B. B sends Rj to what we want to say, to okay, I don't want to write down directly what the B, because I don't need this. Because no, here it's again some model in this direct sum, and so it in fact has some first coordinate. I don't want to check the first coordinate because I only need the second coordinate. Okay, let's remember this, and we will not need this first coordinate. So okay, let's remember this thing. Okay, and now, if we have this beginning of projective resolution of short Ext sequence, then we apply hom to n, and again obtain short Ext sequence of hom, and then long Ext sequence of its homologies. Let write it down. Remember something like remember this. If p sum alpha gi in kernel of d minus 1, kernel 2, then alpha I is in fact of this form, rho gi sum beta g. Okay. Okay. Now I apply hom to n. And want to understand what the boundary map in connecting homomorphs to mean long Ext sequence homologies. What this boundary map? I apply hom to this short Ext sequence of resolutions. If I apply it, I obtain something like.
At first, I thought that when you showed the definition of ID goes to
yes.
I thought that this calculation would be much better and coordinates free, but it seems that
no.
Worse is mine.
No, now I don't. I'm not proving now that that this is bijection. I'm proving that this definition coincides with that definition.
Yes,
so it's.
I understand that.
No, that definition with coordinates. So I need some coordinates in, because I guess I check that coordinate and coordinates free definitions coincide. Okay. You can check after this. It's maybe another exercise that coordinate free definition without coordinates. You can directly check that it's bijection. Maybe you can check this without coordinates. In fact, it's just no. If you want coordinates, you can. Now I write down coordinates free definition in coordinates. Okay. So we obtain hom from F n hom F n hom P n, and I calculate homologies and obtain long Ext sequence. And I need this is 0 homologies of this one goes to first homology of this one. This is isomorphic to hom from M to N. This is Ext. Sorry, from N to N. Okay. Now let's see this. Okay, let's start with identity here. I have identity n to n. What's the class of this home? No, it's just I have this map, and this is just composition. It's always cycle, because I have no further differential. And this is this map. We know this is isomorphic, but if I, but this map is obvious. This is this map. Okay, it's precomposition. It's P0. Okay. No, so it's identity. So it's just d minus 1n. So this class, the homological class of this homology is just d0 n itself. Okay. And now what the boundary map? Now how it works in general. I have what on 0, yes, for example. No, okay, 0, 0, 0. I have element from here. It's surjection, so I have some preimage, and then I just need to consider the boundary of this preimage, and this will be an element here. It's definition of boundary map. Okay. It's boundary map in a long homological exosequence corresponding to short exosequence of chain complexes. I have element from here, cycle. I consider preimage, consider the boundary, and this boundary, in fact, from here. Okay. Now let's do this. I need some preimage, so I need some pi0 plus f0 to n, such that this composition is my given map. Now I can consider stupid preimage. It's just map which is d minus 1 plus 0. Okay, it's just 0 on f0. It's preimage. It's preimage. Okay, I'm just splitting. Okay, and now I consider this map. It's maybe not cocycle here, but I need to consider its boundary in this chain complex. So I need to consider composition of this map with this little bit mysterious map. A little bit mysterious map. So I need to consider P1 plus F1. It goes to P0 plus F0. And then it goes to n as d minus 1 and 0. And this is somewhat d0, this is this map. And then, okay, what is it? What is it in fact? Now a little bit useful how we can think about maps between direct sums. It's just matrices, yes? If you have direct sums of modules, and you consider A plus B to C plus D, yes? It's just matrices. You don't need that they are free. In general, it's 2-on-2 matrix. Any such homomorphism can be write down as matrix A, I don't know, maybe no, A, B, C, D, alpha, beta, gamma, delta, which acts on AB, and you obtain CD. What does it mean? This means that, no, in the usual matrix multiplication, but it makes sense if you means that alpha is just element from home from A to C, beta is home from B to C, yes, and so on. Gamma is home from alpha A to D, and delta is home from B to D. No, it's more or less obvious. Any home from direct sum to direct sum, it has such expression. No, I have this situation because. So I have my map, D0, I don't know it. D0, some alpha, beta, gamma, delta. And then I consider its composition with map d minus 1 minus 1 n 0. This means that I consider d minus 1 0. Now let's multiply these matrices. What is composition? I obtain what I obtain. I obtain d minus 1 alpha, d minus 1 beta, yes? Because it's 0. Okay. And in fact, yes. And in fact, this is 0 because this first coordinate, it's home from P0 to P1. No, it's just differential. It's just differential d minus 1 for n. And this is composition of these two d1, d0. This composition of these two differentials. So it's 0. No, it's again, we just check that if I consider element from here, cycle, and consider preemption, then consider boundary, this map is in fact from here. It's in fact just one map from f1 to n. We have no other coordinate. It comes from here. It comes from f. It's just a definition of boundary map. No, it's true. So we obtain only one map from P from P1 to n. No, from 1 second. Yes, from P1 to n. No, from F1 to n. Yes, sorry, from F1 to n. We obtain this map. No, so we obtain some homological class. In fact, it's cycle. No, it's cycle because we know that homological Ext sequence is correct thing. I only want to say that it's exactly what we obtain here, by definition, more or less. Okay? No, so to understand this, we only need this one coordinate of this differential. It's what I said before, that I, in fact, don't want to understand whole differential g1. I only want to need one quarter of it, one coordinate of the fourth of it, because only these coordinates, important for this composition, for this boundary map. Okay? Any question?
We'll just calculate it. Let's calculate it.
Yes. So this is 0. So I obtain that this map is d minus 1. And so what I want to say that by definition, this map from f1 to n is just by definition this class is my xi. I only need to check that it's an image of my identity, and this is a class of ext1. I only need to check that this map has that explicit formula which I gave you before. No, okay. So we need to understand what this b1 coordinate of d0 of this form, what does this mean? This means that I consider just element rj, and it goes from d1 to something p something, and then I forget this and consider only this part. From, oh no, sorry. 1 second. No. Contrary. I forget this part and consider only this part, and then it goes to n. No, more or less. No, more or less. No, from this observation, it's more or less obvious that this rj goes to rho ji xi. Okay, maybe a little bit more unwinding of definition, but it's now maybe it's more or less a little bit less mysterious that this coincide, because we have this direct calculation, and in fact you only need to understand this differential. And we have some calculations. We consider some element from kernel. It's some of this form. It's where these coefficients appear, and in fact you can check that yes, you can find this lift. No, because we need. Yes, I recall that we need some lift. No, you can choose this lift of this form. It's okay. So in fact, all these not unique choices, in fact, now they are in correctness more or less of the long sequence of homologies. And if you know this in general, then all these choices, no, they are all okay. So you don't need to check correctness of this map from extension to Ext, because all these choices are in the construction of boundary map in long axis homology sequence. Because in this construction of boundary map, you already choose some preimages and so on. And also, yes, and also you need these choices, and you have choice of projective resolutions of some elements. But again, you know that if you know, we know that Ext itself does not depend on resolutions. And if you have short Ext sequence, you can consider any resolutions of these short Ext sequences. No, and so you can consider short resolution or projective resolution of the form of direct sum of projective resolutions. You can consider any other projective resolution, but you can consider this direct sum, and you can consider some explicit differentials of this form, and you know that final result Ext does not depend on projective resolution, and boundary map in homology only does not depend on choices of what you did before. So in fact, this correctness falls from this. Okay. Okay, I think we will finish here. Okay, it's now very much easier exercise to finish this proof and obtain the final part. This is just this thing for some choice of beta, and for some choice of beta of this differential. Oh, sorry, of this differential for X. Okay. And if you use injective resolution, you obtain the dual definition. No, and you can show us that in fact opposite direction. That if you have some xi, this thing is extension. And in fact, of course, you also need to check that these bijections are inverse to each other. Yes, something like this. Okay, now show us something.
Now we need to create a map extensions.
Mm-hmm.
To a set of sequences.
Mm-hmm.
So it goes like this. We need to choose the representative. So first we take a homology class in Ext. Yes. And we just take this representative, and as you said already, we construct a module which is defined like this. We take n, take the direct sum is f0, and then divide by all elements of this sort. I mean, by some ideal generated by all.
No, yeah, submodule generated, yes.
Forms. What?
Submodule generated. It's not ideal, it's
Yes,
not on the
yes,
ring, it's
yes,
submodule.
of course. So J, D0 of RJ.
Mm-hmm.
This is the
Mm-hmm.
definition. So I use notation with
Yes,
players. You
Yes,
use
okay,
plus, but
okay.
I prefer this one. So then we can define a map I. So to
No, it's just a composition of inclusion of direct sum and then projection on factor on quotient
Yes,
module, yes.
it looks like this.
Mm-hmm.
And also an obvious projection. Not really obvious, but So
No, already here you need to check that this is correct, yes?
yes, but correctness I'll check.
No, okay, no correctness, it's a little bit obvious, yes.
I mean, everything here is obvious, it's
Yes.
just tedious. So first we need to, so I want to check that indeed, if we define everything like this, we get a short exact sequence. And here, so the first one is that we need to prove that, so I'll prove that I is injective. Yes. To prove that we need to consider some element, and so by definition this is 0. We consider some element that goes to 0. Yes. By definition, this means that this must be a guy from the factor, from the quotient. And this means that there exists R from 1 such that so basically 0 equals to Okay, I'll write here. So from this we obtain that psi of R is equal to n, and d0 of R is just 0. But since this is 0,
No, yes, then R is d1 of something, yes?
yes.
And Xi and d1 is 0.
R lies in the kernel of 0, which is nothing but image of d1. And this means that there exists some element S from F2 such that this R is d1 of this element. Yes. And but that means that n from one hand this is psi of R, and if when we substitute this formula here we obtain that this is
And psi
just,
of
zero.
d1 is 0, yes?
Yes,
Okay,
because
so
this is
yes.
from homological.
So it's injective.
Yes.
No, pi more or less obvious is surjective because it's yes. No, pi is surjective. Okay, it's obvious. And let's check that kernel of pi is the image of phi. Yes.
Yeah, this is obvious, and
No, because d minus 1 is surjective. Yes. It's just d minus 1 of something. Yes. Pi. Definition of pi. D minus 1 is surjective. So yes, it's more or less obvious that it's surjective.
of course, this is competitions of two surjections. Okay. Yeah, alright. So we need to prove that image equals the kernel in one direction.
And again, it's obvious from your definition. If your definition is correct, it's obvious that composition is 0 because pi is d minus 1 of the second coordinate, and second coordinate is 0 in your definition. So
So this is what you said. Basically, let's just like this. This is by definition pi.
of n 0, and pi is d minus 1 of the second coordinate. Yes, it's okay.
And since it is homomorphism, it is zero.
Yes. The final part to check that in fact it's whole kernel. Yes. That n is the whole kernel. Yes. Okay, let some element in kernel.
Other direction. Let's take some element from the kernel. Yes, and so this by definition this means that if we yes, by definition I mean, if we use pi here, we obtain that d minus 1, then g is filled by d minus 1. Yes. And this means that g lies in the kernel, d minus 1. Yes. But then, once again, we use that image equals to kernel. Yes. And this means that there exists some element R, another element R from F1, such that G is so the image, lies in the image of 0, and this is this. So now we just substituted into the formula in our form of in our initial form of our element, and obtain this, and then we can split this into two summands and obtain 0.
No, maybe you can do this without splitting. Just move this from the right to the left by your. No, okay. Do what you want. Okay. No, the second sum is by your relation. Yes, it's just minus CR. Yes, something like this. Yes.
Yes, yes, yes.
No, I just say that you can do this without splitting. Okay.
Maybe.
No, okay. No, if it's yes, more intuitive, then let's do this. Yes.
This is psi of R, 0 plus minus psi of R
0. The middle term is 0, yes, and so we obtain yes. We obtain something from.
This is I of minus psi of R.
No, yes, and so we into the image. Okay, yes, yes, okay.
So we have equality here.
What about that? These bijections are inverse to each other. I think it's also not very hard. I think the most tedious part is the correctness of this map.
Yes, by the way, we need to prove that this is correct. I forgot about it.
Ah, correct. Yes. Okay. Yes.
This is just small calculation.
No. Yes. Let's check that if you consider cycle which differs from original one by boundary. Yes. You obtain the isomorphic extension. Yes.
Yes.
Okay.
Now we need to just check that these maps are this map that we defined, which sends psi is correctly defined. So now we need to take another representative from our class. This means that prime is psi plus some boundary of some element in the yes. And so let's take phi and define it as a map like this. So this is n plus a0, and it goes to so isomorphism, and it is defined like
It's kind of shift. Yes.
yes. So
No, I think something like n plus eta g. Yes.
Eta g, yes, of course.
Eta is from h0 to n. Yes.
So we need to check that it sends
After
images to image.
yes, if you consider quotient, then it will be an isomorphism. Yes.
Yes.
And
we need to check that this map sends images to images. So, but this is just by definition. We consider something from not images to images. I mean relations.
No, yes.
To relations. Yes. We consider. An element like this. Yes. Then use the definition. This will be This is just by definition. Like this. So, and obviously, so this means that I don't know, we define exercise like
No, okay, okay. Yes, we obtain some module map from our extension to our extension. No, it's not very hard checking that this is isomorphism and it's identical on n and on m. Okay, I believe you do this. Okay, okay. Let's finish here. Okay. What about bijections? Okay, we obtain this. It's true that this map it's an answer. This map induces an isomorphism of extensions. Okay, what about bijection? Because we already have not very much time, and maybe I want to discuss something else in this seminar. At least maybe examples for abelian groups.
maybe.
Or maybe, I think, okay.
For example, I calculated some torsions and Ext.
Okay.
Yeah, we need to check that. So as for this map, I only check that phi with this psi, yes, is identity. So I only checked.
It's just identity. It's just, yes. No, it's more or less obvious from this explicit definition. If you apply phi, you obtain the same size. It's identical on size, on homomorphism. Yes, something like this. No, yes, if you consider some concrete pre-images, then it's identical on psi. You obtain the same psi which you said before. Yes, not class, it's just the same psi. Yes, yes, it's more or less obvious. In opposite direction.
In opposite direction, I haven't done it, but I think.
Okay. No, the opposite direction is to check that. Yes, if you consider some extension, you obtain psi, and then
they will be.
They are isomorphic. Yes.
And we need to prove that they are isomorphic, but I struggle to find the concrete formula for isomorphism.
Okay, let's refine it. Okay, what we remain to check? Okay, thank you. What we remain to check? Don't forget that you have Petlichka. What we remain to check? No, check coordinate free check. Coordinate free check. That coordinate free psi, which we or phi from extensions to Ext1. It's phi, yes? Phi. It's phi. I think it's phi. From extensions, from extensions to Ext. Yes. To finish the proof that it coincides with coordinate definition, which in coordinates it gives us which we defined before, and check that maybe in coordinate-free way, check that it's inverse to psi, maybe. Okay, the second part may be more interesting because we have that this is abelian group. We have some here, yes. So we have some abelian group structure on extension. What is this abelian group structure? If we have two extensions, it corresponds to some classes, then some of these classes corresponds to the so-called Bayer sum of extensions. Bayer sum of extensions. It's defined in the following way. Let me consult my formulas. No, I give you this formula in conjugate-free manner. Don't. Okay. Okay. Yeah, just consider. I have x1 m, x2. I can consider the so-called pullback. Yes. what is it? Y. Y. No, what is it? It's just submodule of direct sum. It's submodule of direct sum. So it's pairs x1, x2, which goes to the same element in M. Pi 1, pi 2. So, and also we have projections to x1 and x2, and it is square is commutative. Okay, it's y, and we can consider in this element in this module anti-diagonal. We have also injections of n. No, we have injections to x1 and x2. We have in okay. This consider this map. Its injection n goes to if it's pi 1, pi 2. And I1, I2. And I consider I1n minus I2n, something like this. And I consider quotient. No, and yes, and consider a quotient. And quotient. And this quotient is x to 1. It's quotient by this anti-diagonal. And in this quotient, you can check that, no, in this quotient, the class of I1, 0 equals to class of 0, I2. Yes? No, it's by definition. So we have only one inclusion of n now in this quotient. N to x1, 2, its n goes to one of these things. And this is our extension. In fact, you can check that this injection and the quotient is m. And this corresponds to sum. This corresponds to sum. It's Bayer sum. Bayer sum.
Is it useful?
No, it's useful because if you, for example, know that, if you know that extension is something like cyclic group, you can consider extension which corresponds to generator, and then you obtain any extension of any element of extension. No, I don't know. No, it's just fact. It's just fact that you can formulate the sum in the terms of extensions. No, I think if we very well understand phi and psi, it's not very hard, I think. Okay. No, it's not very hard to, for example, obtain that from this extension you obtain sum of homological classes.
It's just by definition.
Maybe, yes, more or less by definition, you only need to check that. Also, it's not very hard to check that it's extension. It's relatively easy, yes. Another thing, in fact, what, as I said before, we have coordinate-free map from extension to Ext1. Okay, but consider extension of some length. Example, consider extension of length 2. N, x1, x2, m. Then this extension, exact sequence of this form. I can split this exact sequence on into two short exact sequences. N, x1, co-kernel of this map, quotient. And in fact, this quotient embeds to x2. And quotient is m. It's more or less equivalent thing, okay? From exactness. And now, okay, apply hom to n. Again, I have boundary map hom n from the first short exact sequence. I have boundary map to Ext1 x1 n. It's boundary map for the first short exact sequence. And from the boundary map from the second short exact sequence, I obtain the second boundary map to x2. Now from m to n. And now I can consider this identity and obtain this class. And in this manner, you can obtain, if you have extension of length R, you obtain element of Ext R. And this is bijection, also bijection. So higher Ext is just extensions of the higher length. It's sometimes called Yoneda definition of extensions group. So all of them are extensions group. So Ext R Mn in bijection map of set of extension of length R. You only need to and this map is this map. No, this map is something else. You only need to say what the equivalence here. In fact, let's observe. Notice that if we have extension of length 1, our usual extensions. What if I have two such extensions? Let I have map from X to X such that identical on n and identical on m. Then, in fact, it's automatical isomorphism. I said before that we consider isomorphism, but in fact it's just morphism because it's from 5 lemma. If I have identical, it must be isomorphism. For general extension, it's not true. It's not true. And in fact, in general situation, you consider the equivalence relation, which is generated just by any map. You say that two extensions are equivalent if there exists a map from one to another or in opposite direction. They are equivalent, and then you consider the minimal equivalence relation which contains this relation. No, so two extensions are equivalent if there exists zigzag of maps from one direction to another direction between them, something like this. These maps don't need to be isomorphism on xi. They must be identical on n and m, but some maps in the middle terms. And this equivalence relation, and if you consider this equivalence relation, this will be bijection. And also, this abelian group, you have some Bayer sum and so on. And one interesting thing, from this, you can obtain one thing. If you believe into this Yoneda definition, then, no, in fact, to do what I need to say, you only need this map only into one direction. Oh, no, sorry. Yes. Okay, what I want to say. If you have two extensions, of length R and of length S. And extensions of this form, mk. Now then you can glue them together to one extension from n to k. Now it's just one extension xr. It goes to m. M embeds to y1, and then another extension, and obtain exact sequence. And so, if we believe that it's Ext groups, then we obtain Yoneda multiplication on Ext groups. We obtain map from Ext R M K. No, then the product is because it's bilinear, in fact. It's multiplication. Sorry. From K to Ext R plus S. Okay. Oh, maybe yes, maybe a little bit more natural to write down in this order. Or not. Okay. Sorry, wait. It's true. Mn, Km. What? Then it's natural. Km, Mn, Kn. No, it's just it's generalization of composition of Hom. If it's 0, 0, it's just composition of Homs. And this generalization is multiplication in cohomologies of something. Ext is cohomology. It's multiplication. It's cup product or Yoneda product. And you have, no, at least strictly what we proved so far, we proved that it's true for extension 1. So we, at least we have Ext1. We obtain extensions. From 2 extensions, we have extension of length 2. And from extension of length 2, we have Ext2. So we have something like, we construct squares. No, in fact, it's true that we can construct any multiplications of this form. No, yes, and also it's true that, for example, you can act by home. For example, if you have home, yes. No, it's more or less obvious, in fact. You can check that you have something like this in general. You can move from home from the left and from the right. It's unit multiplication. Multiplication on home, on Ext. On Tor, multiplication on Tor, it's much more subtle story. Okay. Now I have 2 easy exercises and examples of extensions. Now easy exercises, but maybe it's important. What about, for example, Tor Ri Rj as a morphism of this thing.
No, I haven't calculated it.
Yes, you как будет потратить? You spent all your strengths on check of the correctness of extension. Yes. Okay, and also exercise. Okay, then it's exercise. Let it remains. I leave you to the next seminar. And another exercise that, for example, if you consider polynomial in 2 variables and consider ideal generated by any polynomial without constant term. It's ideal, so it's module. This module is torsion free, obviously, but it's not flat. It's not flat. No, maybe let's check this now, because it's more or less поучительно. In fact, if you consider polynomial in 1 variable, then it's principal ideal domain, and over principal ideal domain, it's true that finitely generated torsion-free modules are flat. So it's crucial that it's 2 variables is not principal ideal domain. And this is ideal, which is not principal, and so. Okay. Now let's consider. No, in fact, also we checked before on the previous lecture that over Noetherian rings, over any ring finitely presented and flat model is projective. So this is not flat, and so this is not projective. Maybe you can check directly that it's not projective, but now let's check that it's even not flat. Okay. All projective are always flat, but over this ring, any finitely presented model, not very big model. If it's flat, then it's projective. It's not projective, but let's directly check that it's not flat. To check this, consider its free resolution of this ideal. Oh, no, it's not. No, this ideal. Okay. Let's consider free resolution of K itself. Field K is module over this polynomial ring where X and Y acts by zeros. Okay, it's trivial module. No, it's module over polynomial ring where X and Y acts by zeros. X and Y act by zeros.
Okay.
X1 0, Y1 is 0 in this module. Okay, and scalars acts as usual. Okay.
Okay.
So it's module, and what is its free resolution? No, okay. No, I have, it's generated by 1. It's cyclic, so we have 1-dimensional free module of our ring, no, which sends X and Y to 0 and 1 to 1. No, 1 to 1 it's always true because we can consider Okay, yeah. Let's see. 1 to 1. It's surjection. What is the kernel? Its kernel exactly this ideal. Okay. Kernel is polynomials without constant term. So its kernel is exactly this ideal. Let's denote it by I. And now we can start projection resolution of this ideal. This ideal generated by two elements, so we can consider two-dimensional free module, yes? Which sense? No, in fact, what here I can use here, I can say it here that only one goes to one, and then say that this is a map of modules over polynomials, because then property that x goes to 0, no, because x is x on 1, it goes to x on 1, and it's 0 by definition. Okay, because all these maps are maps of R modules. Okay, so I only need to say there that 1 goes to 1. And here, no, I can check that 1, 0 goes to x, and 0, 1 goes to y, and then by R linearity. Okay. No, then by definition, pair fg goes to xf plus yg. Okay. And this is a surjection, and this is its image is exactly the kernel. So, what the kernel of this map? What the kernel of this map? If I have xf plus yg is 0. xf minus yg. F and g is polynomials in two variables. Now this means that right hand side is divided by x. This means this g is divided by x. Okay. So in fact I have x g g prime is not derivative of g tilde. On the other hand, left hand side divided by y, so f divided by y. So in fact I have xy f tilde, and I can divide it by xy. No, okay, and obtain that f tilde is equal to minus g tilde. And so in fact, my element from kernel, my pair from which goes to 0, has the form that fg from the kernel has the form я забыл чего, y f minus x no, okay, h minus h. If it's h, it's one polynomial. Okay. Only this is only such pairs goes to 0. Okay. No, all such pairs goes to 0, but only such pairs. Okay.
No, I understand. Should we include minus in h?
No, I denote h f tilde. No, if I have pair of polynomials which goes to 0, then first polynomial is one polynomial x, and the second polynomial is minus the same polynomial x. So in fact, this things is generated by one element. It's y minus x model h. It's generated by this element, so it's cyclic. So we have its image is the image of one-dimensional module, which sends 1 to y minus x, and any other polynomial to this polynomial. And this is surjection on the kernel. And in fact, this map is injection. So in fact, it's the end of free resolution. In fact, further, we will prove that over polynomials in n variables, there always exist free or projective resolution of length n. So it's not a coincidence that it is exactly of length 2. It's Gilbert theorem of syzygius. Okay, we see that this model have free resolution of this length. Okay, and we have this difference. Let me write down it again. It goes 1 to 1. One to x to y, and 1 to x minus y, yes. No, y minus x, okay. Okay. Now let's apply to this tensor product with I. If it's flat, then it will be exact again. Now let's see that it's not true. Tensor product over polynomials with our ideal I. What we obtain? In fact, exactness will be distracted already here, something like this. Now let's see this. What I want to say what the k over polynomials tensor product with I. What is it? It's 0. Because any tensor, its element from our ideal. Element from ideal has form x something plus y something. And if I consider tensor product property, yes, it goes x. It's polynomial ring. It's a commutative ring. So h plus. No, sorry. Phew, it's not true. Sorry. No. It's sorry. It's not 0. Because this element, you want to say that okay, this is x1, 1, and this is 0, yes?
Yes.
But this element is not an ideal. This element is not an ideal. You haven't this element in ideal, so you cannot move this from right to left because this element is not x on something in ideal. It's just undecomposable element. Okay? No, if you have x on something, you can move by tensor product property, but it's not x on something. There are no unit in ideal. Okay? There are no such element. So it's just some element in this tensor product. It's not 0, in fact. No, okay. Now let's apply tensor product with I. Все равно. We have this thing. Do you understand that it's not clear that it's 0, yes? You obtain the struggle. It's clear. Yes, it's important. If you consider, for example, k. No, I don't know. No.
I understand what you are trying to say. But
Yes. No. Yes. It's not 0. Okay. And we have no. It's true that over any ring, tensor R, it's something. It's model itself. So it's just I plus I, and then I. Is this exact sequence? Is this sequence is exact? No, sorry. I forget one. I. Okay. Yes. What the map here? What maps here? It sends alpha to 1 alpha. Okay. Here it sends beta gamma to, but here it sends to x beta plus gamma gamma. Yes. Okay. Okay. No, and here it sends delta to y minus x. Okay. Yes. Now you can check, for example, that what the image of this map. Okay. let's leave you to the next time exercise. No, it's true that it's not flat, and I believe that it can be verified on this exact sequence. So this sequence is not exact, but I forgot how to do this. Sorry. Okay, this next exercise is not flat. Some another exercises. Another exercises, it was something like if you have so for example, you can did you calculate some Tor and Ext? Yes. What is Ext between Zn and Zm? First text.
And this is a question. Z tensor. So no, it's Z GCD or.
Yes, it's Z modular GCD. I will denote GCD by these brackets. Okay. Exercise. No, just for example, for Ext1 from Z P prime to Z. What is this? It's Z modulo P. Yeah. It's Z modulo P. It's Z modulo P. And so consider what extensions correspond to these elements. Just как это? Write down P extensions. P extensions. Extensions of the form from Z to something to Z modulo P. It's one question. It's the easiest one. The second one is Ext from ZP to Z modulo P. It's also Z modulo P. And what this is extensions of Z modulo P to Z modulo P. And the final one, Ext from not prime. For example, Z modulo P prime. So Z modulo P prime, they are a little bit more extensions, тоже extensions. No, also you can check, for example, Ext Z modulo 2, Z modulo 3. No, for example, two different primes. If it's different prime, it's 0. It's only one extension. I mean, for example, Z modulo 6. Two coprimes, for example. This is easiest part. This is a little, this is not so much extension. There is a little bit more extensions, but not so much also. No, in general, it's a little bit tedious. It's the simplest examples. Oh yes, and one final part. What extension corresponds to 0 class?
I guess trivial.
What is trivial extension? It's direct sum. Yes, it's true. Zero corresponds to trivial extension. So you have zeros here, and you have p minus 1 non-trivial extensions here, p minus 1, 2, p squared minus 2. But here, in fact, p minus 1 is more or less, they are similar. And here you have two not similar classes of not trivial extensions. You can check this. Here also. Okay, yes, and flatness of this thing, not flatness. Tor 1 between R modulo I, R modulo J. I think. Yes, and we have that Pontryagin duals reflects exactness. That
yes, I forgot.
ABC is exact if and only if the Pontryagin duals exact. You can also check this. Yes. It's a home to over abelian groups to Q modulo Z. No, it's model of circle. No, in fact you can. It's true for circle also. So it's okay. No, okay, then, okay, let's take a break.